All right, so our next presenter is David Woodson. He's from University of Colorado Boulder in the Civil, Environmental, and Architectural Engineering Department. So you can go ahead and take it away, David.
All right, thank you. Yep, so I'm going to talk about the research that I've been working on for the last 9 months or so here at CU, and the project is temperature-informed streamflow forecast for the Upper Colorado River. So just a brief outline of the presentation today, just some background on the Colorado River Basin and associated flow temperature relationships. The method that I developed, titled the K-Neighbor block bootstrap flow forecast. Some results from a flow hindcast period and some operational testing, and then final concluding thoughts. So just some background on the Colorado River. It's a water source for over 40 million people in the western US and northern Mexico. It's also important for agriculture, recreation, industry, and ecosystems. And you can see the basin map here on the right. And specifically, we focused on the upper basin since it produces a majority of the stream flow for the entire basin due to the high elevation headwaters like the Rocky Mountains. However, a high variability in annual or year-to-year flow paired with drought cycles and the multi-year storage capacity built in the basin like Lake Mead and Lake Powell has led to a need by water managers for midterm forecasts, or basically forecasts of river flow for the next 1 to 5 years. And kind of exemplifying some of those issues is this graphic of Lake Mead pool elevation by month. And you can see, in the 1950s, there's this period of pretty bad drought, as well as in more recent years, since the year 2000, the drought that caused a big decline in storage in Lake Mead that really hasn't been recovered from. And so one method that's been used pretty often is Ensemble Streamflow Prediction to produce these midterm forecasts. And basically this graphic shows the idea behind it, where you have current basin conditions and you have an ensemble of streamflow predictions that you put forth. And generally, the ESP has been shown to be skillful in year 1, so it provides a good seasonal forecast. But it often goes to climatology after year 2. And it also has been shown to give equal probability for warm and cool years, which is a potential issue for temperature sensitive basins like the Upper Colorado River. As you might expect, a lot of the river flows from snowmelt, and so temperature plays an important role in how much flow is produced. So a lot of people have looked at, upper basin flow sensitivity to temperature, and that's where I started as well. And basically, this plot just shows upper basin annual flow in million acre feet versus annual mean basin temperature in degrees Celsius. And the points are color-coded by which decade they came from. So these bluer points are from the early 20th century, and then the red points are from the last couple decades. And generally you can see, as temperature increases, flow generally decreases, typically due to things like higher evaporation. And then also as temperature decreases, flow is generally higher. And just generally based on, the timing, we can see that recent years are both warmer and drier. So basically these red points, from the last 20 years or so are all kind of clustered, from like 7 to 9 degrees Celsius. And then a lot of them are below sort of the long-term mean of 15 million acre feet. And looking at 5-year means for these variables, the relationship persists. So this bottom plot just shows the 5-year average annual flow versus the 5-year average annual temperature. And in fact, the temporal pattern appears a little more distinct, with sort of a greater separation between the more recent time series, the last couple decades, and then the early 20th century period in blue. And another sort of known component of the Upper Colorado River is the wet and dry regimes that it goes through. So this plot just shows annual flow for the Upper Basin. And one such example of a wet regime is this period in the 1980s where 4 years in a row flow was way above average. And then an example of a dry regime would be this period in the early 2000s where you had about 5 years where flow was quite below average. And so in addition to exploiting this sort of epochal behavior, we were looking to exploit multi-year autocorrelation for the forecast through usage of these 5-year means. And so going into the method, again, this k-nearest neighbor block bootstrap method, we decided to go with the k-nearest neighbor method, which is a non-parametric approach. It's been used fairly often in past hydrologic studies. And we use this k-nearest neighbor resampling of 5-year flow blocks based on 5-year mean temperature from a climate model. And so just a brief overview of this algorithm, the data inputs were basically community earth system model, or CESM large ensemble, monthly 2-meter mean minimum and maximum temperature for the Upper Basin for 1920 through 2080. And to extend the record back in time, we paired it with community earth system model Last Millennium Ensemble, same parameters, min and max temp for the Upper Basin, but this extended it back to 850 through 1920. And then for flows, we use naturalized Upper Basin flows for 1906 through 2017, and then also paleo reconstructed basin flows for 850 through 1905. So we had a nice long record to sample from. Data processing basically just involved aggregating monthly temperature data into seasonal averages, calculating running 5-year means on the flow and seasonal temperature, and then calculating anomalies on those 5-year running means. And then we split this data set into a training and a hindcast period. So the training period was 850 through 1990. The hindcast period was 1990 through 2017. And then basically we did these running 5-year forecasts for the entire hindcast period with the training period iteratively updated with each step forward. So what one of these 5-year forecasts would look like is basically, you select a 5-year period for your flow forecast. So say you want a flow forecast for 1994 through, or 1990 through 1994. You get the 5-year mean temperature anomaly for that forecast period in a selected covariate. So maybe you use the anomaly of the 5-year mean winter minimum temperature. It finds the k-nearest neighbors in the training period and selects corresponding blocks of 5-year annual flows. And then it randomly samples these 5-year blocks from a list of k-neighbors to generate a k-member annual flow ensemble for that 5-year period. So I'll move into some results. So basically a skill analysis of many different covariates during the hindcast period yielded 2 best models. The first was the winter minimum temperature. The second was the winter and spring minimum temperature, which these make sense also from like a physical basis. If you think about, sort of snow formation or snow melt, these time periods are important for that. And basically this plot just shows the continuous ranked probability skill score, or CRPSS, for both covariates. The blue is the winter T-min, the green is the spring and winter minimum temperature. And it's broken down by forecast year, so years 1 through 5. And basically, if the CRPSS is greater than 0, the forecast method performs better than climatology. If it's equal to 0, it performs the same as climatology. And if CRPSS is less than 0, it performs worse than climatology. So you can see for year 1, most of the simulations from the hindcast period perform pretty well, especially for the winter minimum temperature. Decent performance in year 2, and then as lead time increases, skill generating decreases, but some of the simulations perform pretty well still for years 3 through 5. So next, I'm just going to cover a case study of the early 2000s hot drought. It's called the hot drought because temperature played a big role in the lower flows. And so this plot just shows a 15-member annual flow forecast ensembles from the best models for that period, 1998 through 2002. And basically, it's annual flow on the y-axis versus time. And we have our winter minimum temperature model in blue again, and the spring and winter minimum temperature covariate model in green. And this is compared to climatology, a 30-year flow climatology in gray. And then you can see the observed annual flows, this red horizontal line. And you can see for years, basically years 1 through 4, the observed flows are captured by the model. Year 5, 2002, when flow was just over 5 million acre feet, the models don't capture that, but it's a long lead time, so it might be expected. And then sort of stepping forward, this would be like the next forecast block. So now it's like 1999 through 2003. Years 1 through 3, the models do a pretty good job of capturing flows. Year 4, now with the 5 million acre feet, in year 4, the models don't capture it. They do capture year 5 flow, which is slightly below average. And then stepping forward again in time now, we see in the 5 million acre feet 2002 flow is now like the year 3 forecast, and actually the two models are tending towards lower flows, and one of the models does actually capture that observed low flow. Stepping forward another year, so now our drought period of 2002 is again captured by one of the models, and then like decent performance for the other years, depending on the model. And then finally, 2002 low flow is now like a seasonal forecast, and both models are tending towards lower flows for that year, with one of the models again capturing it, and then decent performance for years 2 through 5. And you can notice some of these average flow years, the K nearest neighbor block bootstrap method, it tends to have a tighter range than climatology, which is a good thing as well. So finally, I want to compare the K nearest neighbor block bootstrap forecasts with both Ensemble Streamflow Prediction and climatology in the US Bureau of Reclamation's midterm operations model. And so this plot just shows Lake Mead pool elevation for water years 2000 through 2004. It's from MTOM simulations. And on the y-axis, we have elevation, so pool elevation in feet, and then time on the x-axis. And basically the red line is basically what would be observed, like the observed pool elevation from the model simulations. The black line is just a climatological mean forcing in the simulation. The gray is ESP simulations, and the green is simulations from the K nearest neighbor block bootstrap. And you can see generally the ESP tends towards climatology, with some ensemble members going to these low flows, while the K nearest neighbor block bootstrap, majority of the traces are tending towards the observed low flows during that drought period, with only a few ensemble members, being more towards the climatology, which is a good thing. So just some final conclusions. The K nearest neighbor block bootstrap algorithm shows moderate consistent skill in years 1 and 2, with some ability to capture extremes and some potential for operational use. Some future work I'm looking at is use of high elevation temperature as the model forcing, rather than the basin mean temperatures that I used for the results that I've shown. And some acknowledgements. I'd like to thank US Bureau of Reclamation and CEU Boulder for funding. Note the disclaimer, these has not been formally disseminated by the Bureau of Reclamation, and should not be construed as reclamation policy. I'd like to thank Dr. Balaji Rajagopalan for guidance and administration, Dr. Aaron Taller and Minga for providing me with some CESM data and guidance, and Dr. Sarah Baker for providing me with MTOM model data and guidance. References here, and thank you for your attention. I'd be happy to take any questions and comments.
Great, thanks, David. We do have a question, and that is, have you tried stratifying your data by El Nino or La Nina?
So, yeah, ENSO, I have looked into ENSO a little bit in some other aspects. As far as like the temperature, I haven't. That's probably a good idea. Using that as like another covariate or somehow separating it, I guess. But yeah, this model didn't, the only covariates were basically like the climate model temperature and then some past, like a past 5-year mean flow. But yeah, some sort of ENSO index could improve performance.
Great, and I might just try to turn on Cecil's microphone.
Oh, this is Cecile. Yes.
Cecile, sorry.
No, it's okay. Really, when I looked at your extremes, you could see the El Nino La Nina signal, especially in the early 80s and the early 2000s.
Like some of the flow forecast blocks?
It's not so much your